We all remember that, right? The goal of our class, which is understanding life while building it. Seems I'm too loud. Okay. Can everybody hear me okay in the back? Okay. So the question is always like what to build, right? That's the first thing, and then how to build it. The next question is, what problems with the approach? And finally, whether there's any solutions for that. To determine what to build, we needed to think about what we know about life, you can observe, right? To answer the question how to build it, that will based on not only on what we know about life, but also about chemistries, right? About chemistry of different chemicals, physics, and also, how should we design the experiment to do that? The problems, of course, then we'll see what kind of results, based on our experiments we have, and the solution is on two sides. One is what are the solutions by life itself inside the cells, right? Another solution is what engineering solutions we can have, right? So that's actually part of the reason we're talking about building life, right? That's actually making synthesize of life. We have already talked about last time that we will just focus on large molecules of life, so those including DNA, RNA, and proteins, and we are going to ignore the small molecules essential for life. For DNA is polymers of deoxynucleotides, while RNA are polymers of nucleotides. Proteins are also polymers, but the monomers made protein were alpha amino acids instead of nucleotides, right? So to think in the very basic items, we can, think that the building blocks of life in the very, very small items, all right, are deoxynucleotides, which will be used to make DNA, and nucleotides, which will be used to make RNAs and alpha amino acids used for making proteins, right? So here is your first clicker question. With the clicker question, the longest time I can give you will be 1 minute, right? For this simple one, I'll give you 30 seconds. So you need to input your answer in 30 seconds. Okay? Order? Any problems? Yes? Yeah, so you either choose A or B. No, like the code, like AA. Oh, the sequence of the clicker is AA. I mean the frequency. You okay? Do you need help? I got it. You got it. Okay, cool. So now I can stop, right? Well, let's see. What's your choice? So deoxynucleotides is B. So most of you got it right, right? The difference is just this 2' hydroxy group. You know, when you have this hydroxy group, that's nucleotide, and if you don't, that's deoxynucleotide, right? Here, actually, we're looking at adenosine 5' monophosphate, you know, either deoxy or just nucleotide there. So one is AMP and another is a DAMP. Okay, so nucleotides were made of 3 components: a sugar ring, a base, and a phosphate group. The linkage between the base and the sugar ring is the carbon-nitrogen bond, right, between the phosphate group, and the sugar is a phosphor-ester bond. So to take them apart, to take the nucleotides apart, we have a nitrogenous base. Well, here is just one of them, right? Adenine. And we have the sugar for DNA. Here is the DNA deoxyribose, right? We have the phosphate group. When you link the the nitrogenous base with a sugar, then the product is a nucleoside. If on top of that you add a phosphate group, that makes a nucleotide, right? So you have sugar plus base makes a nucleoside, and the nucleoside plus phosphate group makes a nucleotide. You do need to know these terms, otherwise a lot of things will not make sense anymore. Okay, so this is another view. You have the sugar ring, the base together makes a nucleoside, and if you add the phosphate group, 1, 2, or 3, right, you have the nucleotide. So if one phosphate group is added, that's a monophosphonucleotide. If 2, that's diphosphonucleotide, right? If it's 3, it's a triphosphonucleotide. And we know there are 5 different bases, 4 for DNA and 4 for RNA, where between RNA and the DNA, 3 bases were shared, right? The differences between RNA and DNA bases is the uracil will be used in RNA only, and thymine will be used only in DNA. So can we do our synthesis? You know, we want to synthesize life, right? We want to understand life by building it, by synthesize that. So can we do that starting from scratch? Meaning, you know, can we just, synthesize the building blocks of life, including the sugar ring, the bases, and the phosphate group, right? Let's think about the sugar ring first. So for RNA, we have the D-ribose, right? The ribose is a 5-carbon sugar. You can actually, the sugar will exist in several different forms, as we mentioned on Friday. So this is a linear form. And these 2 are, 5-carbon ring, right? Not 5 carbon, I mean 5 atoms ring, right? So this is furanose, 5 atoms ring, and here is a pyranose, so that's six atoms form the ring, right? So you know, for the ribose, either ribose itself or deoxyribose, it can, you know, in water can exist in all these forms in equilibrium, meaning that actually, you know, it doesn't matter you start with a linear form or you start with a 5 atom ring form or 6 ring form. You will have all of them, right? Because they are interchangeable. That's these symbols mean. They are interchangeable. So you cannot say, well, I only, I will only have this. You cannot do that, right? So when you start with this, even though you synthesize this as a pure sugar, right? When you dissolve that in water, you know, it will be changed. Okay, so when we try to synthesize the, you know, the beta form, right? That's the D-ribose. That's what we want, D-ribose. In all the reaction, people have tried to synthesize the D-ribose, right? Starting from simpler molecules, I would say, like formaldehyde, right? When you do that, you know, not only you get the D-ribose, but also there are other molecules can be formed. These guys are all 5-carbon sugar. The differences between these molecules are just the differences between the, you know, the stereo conformation of one of the carbons, right? So these guys, you know, are really very similar chemically and physically, meaning that their chemical properties and the physical properties, they are very similar. So when you put into the solution, they will interact similarly with whatever reagents they will interact with. These guys, as I said, you know, they differ just in one of the carbon in their stereo form, and actually it's the mirror image of the carbon stereo form, right? So like the left hand and the right hand. So we have when we want to synthesize a D-ribose, you will get simultaneously a lot of diastereoisomers, right? Those guys are isomers that differ in one or more carbon stereo form. And also you will get enantiomers of D-ribose. So enantiomers are the stereoisomers that differ in all of their stereo centers. Diastereoisomers is one or more stereo center, but not all, right? Enantiomers are all. So basically you have quite a few isomers which will be formed simultaneously, and they also have very similar chemical and physical properties. So now we face the problem of homochirality. meaning that, all the sugars, right? The sugar in DNA will be deoxyribose, right? And in RNA will be D-ribose, not any of the isomers of them, right? So we face the problem of homochirality. So you may say, well, let's start from the pure material, right? That's the solution. Okay, so in addition to this homochirality problem, another problem which is called Ashford paradox, that's a phenomenon that actually a lot of experiments have demonstrated that as a rule, that organic systems giving energy and left to themselves will devolve to give uselessly complex mixture, which is called asphalts. That's why this is called the Ashford paradox. Well, I did not make up this sentence. It's a quotation from Banner's article. So we have the homochirality paradox, and we also have to deal with this Ashford paradox. So now can we then resolve the problem, right? Let's not start from the scratch. Let's start from somewhere, a better place. Like, let's use pure building blocks, pure D-ribose, or pure deoxyribose, right? Well, we have already mentioned earlier that even though you start with the pure sugar, the deoxyribose, it will still exist in more than one configuration, right? So that's why I asked you guys to calculate the possibilities of, linking different nucleotides together. Where you say, well, that's just a sugar problem. Well, that's not only the sugar problem, right? If you want to build up bases from scratch, we also run into the Ashford paradox. So in the same condition, a big mixture will be formed, and many of them will have a similar chemical and physical property, and we cannot even, get the pure form. So even we start with the pure basis, right? If we the pure nitrogenous basis, the bases they can also actually form, I forgot the term. So they will also have different forms in water, right? These guys, they are either you start with this or this, you will get both, right? That's what I mean. So with the guanine is even more isoforms there. They are not really isoforms. They can do isoform, yes. So when I ask you guys to do those calculations, right, and supposing that we just mix the basic building blocks, sugars, bases, phosphor group together, what is the possibility? You just by mix them together, wait, and then, you know, the DNA sequence you want will be made, right? So, well, my calculation was, you know, assuming that the genome sequence is made, the one strand is AC, and of course, the complementary strand will be GT, right? When we read the sequence, it's always from 5' end to 3' end, right? So that's our simple genome, you know, with 2 base pairs. 2 base pairs actually were made by 4 nucleotides, right? So to do that, you know, I think because you have already graded your classmates, right, you must have read my answer. So the first thing we should do is to estimate the isomers of the first strand of DNA, right? And then the second strand, and then the ways to combine both. So to determine, you know, about the first strand, which was made by 2 nucleotides, we check for 1 nucleotide first, right? 1 nucleotide first. And the first one is adenine. So you want to ask, well, how many hydroxy group in deoxyribose can be used to form the carbon-nitrogen bond, which is a connection between the sugar ring and the base, right? And then the next question is how many nitrogen-hydrogen bond, you know, in adenine can be used. So we do those calculations, and if we just focus on one of the configuration of the sugar, we'll see that in each of the configuration, right, there are 3 hydroxy groups can be used, and of course we have 5 different configurations. So then the next thing is how many, you know, nitrogen, hydrogen can be used. Well, these two are equivalent, so we don't separate them, right? There's one possibility is the other hydrogen is linked with the 9th position, the N9, right? Another possibility is the hydrogen is linked with the N7. So there are basically for each of the sugar configurations, there are 3 different hydroxy groups can be used, and for each adenine, there are 3 different nitrogen-hydrogen bonds can be used to link the base to the sugar ring, right? Because this is a reaction we're talking about, you know, one water group, one water molecule will be get rid of when you link these 2 together, right? So for this configuration, this isoform of deoxyribose, we can do the calculation, you know, 3 hydroxy group and 3 possible nitrogen-hydrogen bonds can be used. That's 9. And we do the same calculation with the beta D2-deoxy ribofuranols, right? And then do the 3 other configurations of deoxyribose. So the total possibility of making adenine nucleoside alone is 45 choices. Here are some examples of those linkage, right? In those, you know, one of those 45 is this. This is the only thing. This is the only thing actually exists in our natural DNA, right? So that's the only form. So here we have the paradox of, I say, homolinkage. That's the term is made by me. So maybe you have a different thought, but the idea is that, even though chemically there are many different ways of linking a sugarine deoxy or just a ribose sugarine with a base, right? But biologically, inside our cells, there's only one valid choice, right? So the nitrogenous base in natural DNA are always, no exceptions, right? It's always linked to deoxyribose at the 1' hydroxy position of the beta form of D2-deoxyribofuranose, right? Not the purinose. So this is a homolinkage problem. So, within a lot of choices, only this one is used inside our cells, right? This is the problem of homolinkage. Well, you may say, well, did you not show that the equilibrium that, the linear form is a minor, very minor form of deoxyribose, right? But you may also notice that actually the major, the most stable form is the 6' the purinose form, not the furanose form, right? Furanose form, so this is what is used in our DNA. This is what the most stable. And of course, this is the least stable. So you may say, maybe, the problem is not as bad as you said, because at least maybe we can ignore the linear form, right? But remember that, if you have taken organic chemistry, I suppose most of you have, right? Remember the silver mirror reaction? In that reaction, actually the only form is active in that reaction is this form. And when you do the silver mirror reaction, all these forms will be changed into this linear form, right? Because the reaction, drives to a direction that everything will be used as the linear form. So really the stability of the molecule does not always equal to reactivity of the molecules. Okay, so we have done the calculation with adenine, and now we can do the calculation with cytosine, right? So everything else is the same except, the only difference might be the nitrogen-hydrogen bonds. Actually, here in this case, actually cytosine has the same amount of choices with adenine, right? So it's also 3 choices. The total number will be 45. So now the next question is the addition of a phosphate group, right? So the phosphate group can be added, also by this reaction. It's always a condensation between, one molecule and another getting rid of a water molecule, right? So now the question we want to ask here is how many remaining hydroxy group in the deoxyribose ring can be used, right? Because we have already used one to link to the base, right? The nitrogenous base. And what is left for the phosphate groups can be used, right? We have 3 total, 1 is used, so two are left. Here, we also have the problem of homolinkage. Remember that the base can be linked, right, via any of those 3 hydroxy groups. And for the first hydroxy group can be either at alpha position or beta position, right? But inside our cells, the phosphate group is always linked to the nucleoside. So nucleoside is the base that are linked to the sugar ring through the beta position, right? So we have the same problem of a homolinkage, or the possible linkage of a phosphate group to other configuration of, the isomers of nucleosides do not occur inside our cells. So we can calculate the way of linking an adenine and a sugar and a phosphate group, right? That's going to be 90 because there are in each of the deoxyribose form there are 3 hydroxy group, right? And in each of adenine there are 3 different choices of nitrogen hydrogen bond. And then when you link these 2 together, there are 2 ways, two choices of linking the phosphate group. And remember, we have 5 different deoxyribose forms, right? So the total number of joining an adenine, a phosphate group, and deoxyribose is 90. While this actually this calculation ignores all the isomers of D2 deoxyribose that are not a D2 deoxyribose. Remember those, actually many of the 5-carbon sugars with, differs in only like in the sterile configuration of one of the carbon atoms, right? So we don't count any of those, right? So we are talking about all the isomers that of D2 deoxyribose, D2 deoxyribose. And we also ignore all the isomers of adenine that are not adenine, right? Because if you can arrange the atoms in many, 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 many ways. And, those isomers, a lot of them actually can be formed in the same test tube if you want to make the adenine from scratch, right? We also ignore all the isomers of linking the phosphate groups through non-phosphoester bonds. And we have already said that only one of the 90 is a nucleotide that exists in natural DNA. So this is why we're talking about both the homochirality problem and the homolinkage problem, right? Now we have made 2 nucleotides, right? And the next thing is to link those 2 nucleotides together. And now we need to ask how many remaining hydroxy groups in each deoxyribose can be used. Well, only one left, right? And how many phosphate groups in the two nucleotides can be used? Well, in each nucleotide there are one phosphate group, so there are two of them, right? So we can join the two nucleotides together to form either Ca or Ac, right? The order can be different, right? Because actually those reactions, if you calculate the energy changes, they are very, very similar. Okay, well, not only, those two nucleotides will interact to form A, C, and Ca. Remember, in all reactions, we cannot just have two molecules in the test tube, right? We have many of them, right? For each material, we have many molecules. So in addition to form AC and Ca, actually we will also have AAs and CCs, right? You cannot force this molecule that you tell this molecule, well, you have to interact with this, not by yourself, right? We cannot do that. Not only that, the phosphate group can be linked together. And by that linkage, we form a molecule like that, right? So the two phosphate groups were linked together. Guess which one is the major product? Not thinking about anything else. So these 5 different kinds of molecules, which one will be the major product? Any guesses? Is this one? Because actually it's easier to form this phosphor bond than to form these guys, right? So basically this reaction, right, both the phosphor group interact with each other. This is I need to go back too many, so let's just ignore that. Okay, so anyway, this will be the major product. So because many people believe the RNA was, right, RNA would, so actually more researches were done, study, to linking the nucleotides instead of deoxynucleotides, right? Remember, nucleotides will be used to make RNA, while deoxynucleotides will be used for make DNA, right? So it was found that when you join two nucleotides, this is not deoxynucleotides, so I make it clear. When you join two nucleotides together, the frequency of a product, this is the most frequent, right? So to join the phosphate groups together, instead of the phosphate group joined with the hydroxy group of the sugar ring. The second abundant is the joining of the 2' position hydroxy group with a phosphate group. And the least abundant in these 3 is the linkage of a 3-hydroxy group with a phosphate group. Remember, this is what we want, right? This is what we want. But it's easier to form this and this than that. So in a typical oligomeric reaction, This is the typical product you will have. You know, you have the phosphor groups linked together, and you have the 2' hydroxy groups linked, and the 3' hydroxy group linked here. These guys are also linked by 2' hydroxy group, right? You know, look like a 3, but here you can see the nitrogen base is here, so this is the 1' prime position, this is a 2' position. So even start with the pure basic building blocks, you know, the just start from the nucleotides, right? Not thinking about even start with the bases and sugars. Even just start with the pure nucleotides. You know, we still face the problem of a homo linkage because, you know, inside our cells, it's always the 3' and the 5' phosphodiester bonds will be formed instead of a 2', 5' phosphodiester bond or the phosphodiester bond, right? So we have that problem, even starting with pure nucleotides. This, you know, the homo linkage, you know, occurs with DNA, with RNA, and with protein, if you want to look at their synthesis from the basic building blocks. Well, regardless, let's go on with our calculation, right? So the possible isoforms of making a adenine nucleotide here, adenine here, adenine nucleotide here, and cytosine, right? So these are the isoforms of deoxyadenine monophosphate, and this is isoforms of deoxycytosine monophosphate. To linking those 2 nucleotides together, I mean, to make them from, if we start from sugar ring, the bases, and the phosphor group, right? The number is humongous. Aren't you surprised? That's why I asked you Friday, they're giving you a wild guess, right? So that's our first strand. First strand of our genome, the 2 nucleotide long genome. In addition to those homochirality problem and the homo linkage problem, another problem we face actually is a water problem, right? Because even though we know that water is essential for life, however, those polymers actually cannot be formed in water, and they cannot stay stable in water, right? So water is essential for life, and the biopolymers are also essential for life. But if we just put the nucleotides together in a test tube, actually they prefer to separate from each other instead of linking to each other to form polymers, right? Are you with me? Because it's actually the polymers are less stable than the monomers, right? So it's easier actually to break a polymer than to make a polymer. This is a problem with water, right? So, well, let's ignore that. Let's keep on going. And so we have calculated how many possibilities of making those 2 nucleotides long, not polymer, but dimers, right? Because we only have 2 units. So it's not polymer. Polymer is more than 3, right? Okay. Now the next thing is estimate the isomers of the second strand, which will be complementary to the reverse and complementary to the first strand, which is a GT, right? So we can do the calculation. As I said earlier, guanine has actually the most choices of nitrogen-hydrogen bonds. So here to form a guanine nucleoside, not nucleotide, there are 75 choices. Thymine is easier. There are only 2 nitrogen-hydrogen bonds can be used. So if we put everything together, the 4 bases, all right, linking the 4 bases with sugarine and phosphor group, that's the numbers you can get, all right? For adenine is 90, cytosine is also 90, for guanine is 150, for thymine is 60. So the way of making a guanine thymine dinucleotide is 18,000 ways. 18,000 isomers can be formed. Now, the second strand of DNA inside our cells are not freely changeable. So they are determined by the sequence of the first strand, right? So that's why you cannot say, in addition to GT, I can have TG, right? That's not a choice. So that's why here, instead of times 2, actually you needed to divide 2, because times 2 then divide 2, right? So you times 1, because you only have 1 choice there, because the sequence is determined by the first strand, right? So you have less isoforms there, and now you put those together. So the first strand, the second strand put together. Have you ever imagined that many of isomers would be possible? Just when you're trying to synthesize a genome with 2 base pairs long. And here we have ignored all the isomers of, the 2-deoxyribose that are not D2-deoxyribose, and all the isomers of ATGC that are not ATGC, and also the isomers of linking the 2 sugar molecules through non-phosphor ester bonds, right? Okay, so here are a few possible, isoforms that or linkages that you can get by linking, a adenine and a cytosine together. I think I just want to stop here, and we can continue on Wednesday.